Lesson on wave behaviors. It's important to know when a wave undergoes a behavior, its characteristics may change. Characteristics such as the wave's frequency, period, wavelength, amplitude, or velocity. Some of these characteristics may change, while others may not. It depends on the type of behavior. So let's check out those different behaviors of waves. Reflection. There are two types of wave reflection. First type is fixed end reflection. This is when an incident wave pulse travels down a string or slinky, and as it's reflected at the end, the pulse inverts. As you've seen in class, we can take an incident wave pulse, that is a pulse that has yet to undergo a behavior, and have that travel towards a fixed end. As this pulse travels to the right towards the fixed end, let's say it's a positive pulse, as it encounters the fixed end, it's going to change direction and come back to where it came from and head off in a new direction to the left. And we also notice that pulse is negative in amplitude. So when a wave reflects, we can see that its velocity and amplitude may both change. This amplitude right here is slightly lower than the initial amplitude of the incident wave. That's because some energy was lost during this reflection process. But what if that end were a free end or open end, or in the pulse activity, loose end? Then that incident wave pulse would reflect and stay upright. So before we would have this positive wave pulse coming down, you would encounter an open end or free end, and as it encounters that and reflects off, it's going to stay on the same side. It'll still be positive, it might be a little less positive in amplitude due to some energy loss during that reflection process. Interference. This occurs when two waves traveling towards each other collide and then continue to pass through each other. There are two types of interference, constructive interference and destructive interference. In constructive interference, this is where two waves construct to form a larger wave, thus resulting in an increased amplitude that is the addition of both. So if I take two waves here, let's say we have pulse A and pulse B, and let's say A is moving to the right and pulse B is moving to the left. Well, the moment these collide, we're going to form a much larger wave, and that will result in an amplitude of A plus B. Now after they collide, A and B are still going to remain and continue going in the direction they were going in originally. So A is now over here, still traveling to the right, and B is over here, still traveling to the left. These waves simply pass through each other because waves are energy. When waves destructively interfere, these two waves combine and destroy the wave. The resultant amplitude is either zero or definitely less than either wave. So if we look at pulse A and B again, let's have pulse A be positive and pulse B be negative. So here we have A moving to the right and B moving to the left. Now the moment these collide, these pulses will combine and form zero amplitude, thus the wave is destroyed. A moment afterwards, we will still see B traveling to the left and A traveling to the right, as these waves simply pass through each other since they are energy. Standing waves. It's important to recognize that standing waves are not a type of wave, but a wave behavior. It's a wave behavior produced by continuous reflection and interference of waves. It's where those waves appear to stand in place, and the propagation of the individual waves cannot be seen. In class, we saw these on the wave machine, and you'll produce these on a slinky or spring. If you vibrate the spring, you'll notice you will form standing waves of first order, or second order, or third order. You'll notice these standing waves have particular characteristics. That is, places where the wave vibrates a lot, and places where the wave does not vibrate at all. The places where you have maximum vibration are called antinodes, and those are formed by constructive interference. So if we look at this antinode right here of the second order, if we take a little microscopic view of that, we could see that right here to form this antinode, there would be two wave crests meeting and combining, making a larger crest that we see here, or trough. If you notice, the first order standing wave has one antinode, The second order standing wave has 2 antinodes, third order standing wave has 3 antinodes. So the order number corresponds to the number of antinodes. The other characteristics here are called the nodes. This is where the amplitude is 0 and the waves are formed by destructive interference. If you took a microscopic view of the nodes, you would see that that's where a crest and a trough meet and thus cancel out, resulting in an amplitude of 0. In class, you'll make standing waves and determine the frequency of each order and how those compare, and also need to measure the wavelength. To measure the wavelength of any standing wave, we take the distance from node to the next node and multiply it by 2. So for a first order standing wave, from node to node, that's the entire length of the string, and we multiply that by 2. For a second order standing wave, we would have to take this distance from this node to this next node and multiply this distance times 2 to get the wavelength. That would be done for every successive order of standing waves. Thank you for watching, and see you in class.